Hello, welcome. Today we're going to be talking about calculating tangent, normal, and binormal vectors, and also decomposing acceleration into these components. So let's just review some things really quick. What we're given is an r of t, some trajectory, in 3D space. Okay, and we're also we know that r prime is equal to the velocity vector, and we know that r double prime is equal to the acceleration vector. Okay, and so acceleration happens to be decomposable into these parts, two components. There's what we call at times the tangential component vector, and also the an, the normal component vector. And t is just the normalized velocity, like so. And n is the derivative of the tangent vector, also normalized, like that. Okay, together these form what they call the osculating plane. They span the osculating plane. The idea here is if you have some trajectory and you're at some point, the tangent vector points that way and the acceleration vector points towards the direction you're turning in, basically. And these are unit vectors, and they form this plane that the acceleration vector has to exist in. So here, the acceleration vector might point in that direction. But what's important is basically the acceleration can be decomposed into these two components. All right, so let's just do an example of how to find these two things. So AT is the scalar tangential acceleration. So it's a scalar function that tells you basically the tangential component of acceleration, and an is the scalar normal acceleration. All right, so this is really about the throttle. I always call this the throttle or the brake. Okay, and I think of this as turning. How much of your acceleration is due to speeding up by increasing your throttle or by slowing down by braking? So that's how your acceleration, how you're speeding up. And acceleration can also come from turning. If you're changing your trajectory, and again, you can see that with the normal component, it really is about how the tangential component changes side to side. That's given by an. All right, so that's the background. Now let's do an example. Okay, so the example we're going to give is the classic helix. So we have r of t is equal to cosine of t sine of t comma t. All right, in 3 dimensions, this looks like the following. It keeps ascending till it ends up, as it goes around in a circle, it ends up 2 pi higher than where it started in one revolution. So you can see this casts a shadow, basically, that is a circle that goes around the xy plane like that. Okay, so let's figure out how to find the tangent and the normal component, and we'll also get the binormal component. All right, so v, that's r prime, That's, of course, going to be negative sine of t, cosine of t, comma 1. And, of course, a is going to be r double prime. And that's going to be negative cosine of t, negative sine of t, comma 0. All right, so I said that the tangential component is simply the velocity vector normalized. So we need to normalize that. So we're going to take v and look at its magnitude. So that's the square root of sine squared t plus cosine squared t plus 1. That's going to be the square root of... So we know that cosine squared plus sine squared is 1, so that's 1 plus 1, otherwise known as square root of 2. Cool. So that means t is going to be the v vector, which is negative sine t cosine t, comma 1, all divided by square root of 2. Good. The next thing we have to do, now we have to find n, and we know that's going to be t prime divided by the magnitude of t prime. All right, so let's compute t prime. Well, that's going to be 1 over root 2. That will just stay out front. That's just a scalar multiplication. And that, of course, gives us the negative sine, or, oops, sorry, that's going to be negative cosine of t, negative sine of t, comma 0, like this. And now, of course, we have to normalize this. And that's going to be the square root of the sum of squares. So that's going to become 1/2 when we square the square root of 2 times cosine squared of t plus 1/2 sine squared of t. And that becomes the square root of 1/2 times cosine squared plus sine squared, which is just 1. So we get 1 over square root of 2. All right, so that means the normal will be t prime over t prime in magnitude, which is going to be... So essentially the square root of 2's cancel, and we're left with this. Okay, so that's the normal component, and that's the tangential component. One important thing we should note here is that these are orthogonal. So t dotted with n is always going to be equal to 0. Let's just check. Right. Well, it's pretty straightforward to do this check. T dotted with n is going to be 1 over root 2 times positive sine t cosine t minus sine t cosine t. So that's, of course, 0. Okay, good. Right, so now we found these two vectors. Let's just bring them up there. Here they are. There's our two normal and binormal vectors. The next thing we want to ask is then, how do we... The final bit we want to ask is, we want to decompose acceleration into these two parts. We want to find at times t plus an times n. All right, so let's find at and an, these scalar functions. So what's really important here is that we actually know this fact, and that can help us a lot, because what we can do then is say if I dot my acceleration by t, like that, what's that going to do? So now if I have a dot product there, sorry, I have to put that dot there. I'm going to dot this in, and of course I'm going to distribute in to both pieces there. And what am I going to get then? Coming out of that is AT times T dotted with T plus AN of T times N dotted with T. We know that's 0, and we know that this is 1, so that's equal to AT of T. Okay, so it remains to be seen what this is. I'd like to figure out what that is. Sorry, that has to be no, that's good. So we have to figure out what that is, but recall what A is. A is right there. So now what I'm going to do is I'm going to write A dotted with T is going to be a negative cosine of T times comma negative sine of T comma 0 dotted with, and now we have negative cosine of T negative sine of T comma where is it? It should be 1 actually, sorry. Like that. And then of course we have to divide by root 2 everywhere. Okay. If you multiply all these things through, it's pretty clear that it's actually 0. So we've actually figured out that AT of T, that scalar function, is equal to 0. Okay? Right, because we know that was equal to AT of T. Okay, the final calculation we want to do is find AN of T. Well, we're going to do that by dotting N by the acceleration vector. We're going to do the same logic as before. So what we have here, N is going to, of course, be negative cosine of T times comma negative sine of T comma 0. So this is N. And of course that is equal to, and then we have to dot it by acceleration, which happens to be the same exact vector. We dot those together, and of course we're going to get cosine squared plus sine squared is equal to 1. So this is my AN of T. Our acceleration is constant. I think it's worth getting a picture of this going again to just get an understanding of what's going on here. Here's that helix I had before. So, and then at every point we have a t vector going like this. It's pointed slightly up, and it's going around. But the n vector is always pointing in, like that. And it's driving all of the acceleration. So we're not speeding up as we go around this spiral. We're just turning as we're slowly climbing upward. All right. The next question we might ask is, well, what is the binormal vector? What is the binormal? We know it's defined as t cross n. We can simply compute that fairly straightforwardly, but it will always be this. There's b like that, coming out, pointing upward. So let's just compute that really quick. I think that would be a good thing to compute. So t, of course, let's find it over there again. Where is t? I see it. T is equal to negative, what was it again? Negative sine of t, and then we have a cosine of t, and then we have a 1, like that. And then our n, and this is times root 2, 1 over root 2, and n was equal to negative cosine of t, negative sine of t, comma 0. Now if I cross them together, one way to do it is to go ij and k like that, take the determinant. Since you have all the pieces right there, you might as well do it. And that gives me we just have to go through this calculation carefully. That's 0, and that will give me a positive sign of t. Okay. And then we have we have to go now to the j vector. So we make a matrix minor formed by those columns. And again, we're going to have now, we have to negate everything we compute here, though, when we do the cross multiplication. And we're going to get a minus cosine of t. And then finally, to further this, we just have to do one more calculation. Look at the matrix minor formed by there. And we'll see we'll get a positive sine squared minus a minus cosine squared, so that's going to be equal to 1. All right, so that's our example. This is my binormal vector there. Okay, so I hope this is enlightening. I hope we learned a few things about how to use dot products and how we can decompose acceleration into these components, how we can find binormal vectors, all of the above, to compute, mostly to decompose our acceleration vector. Acceleration, of course, is very important because it's related to forces. If you're talking about a trajectory of some object that's changing its trajectory, in our physical world, that's only going to happen because there is some applied force to the system, and that a force is of course translated into an acceleration. And so that's why we want to know and want to express everything in terms of the acceleration and its different components. All right, thank you very much.